Thank you, everyone, and thank you for the organizers and the invitation. I'm heartbroken not to be there with you, but I will say it is 6 a.m. in the morning here, and that perfectly recaptures the feeling of jet lag you get if you travel to Vienna from California and give a talk at 3:30 in the afternoon. There's another nice effect here. You can see the Earth is setting over there. And if you look at the reflection in my head, which I waxed for you, you'll see the sun rising over the other side. So that should be kind of good. A little bit of excitement. I'm going for kind of hybrid style here. I've prepared slides, but it'll be partial blackboard because I'm going to write on them. So let's get to business. I have a beautiful new font for the title here. So quantization of contact structures. Some of this stuff, some of you may have heard me talk about. This is work with Roger Casals and Gabe Herzog. And there's some aspects that were done with Alindo Corradini and Emanuela Latini. You'll be surprised to know it, but the talk has a plan. And that was the neighborhood dog walking past. The talk has a plan. The first half is a discussion of quantum mechanics and maybe formulating quantum mechanics in terms of the kind of geometry that a lot of people at this conference like. More generally, it's thinking of quantum mechanics in a way that's very generally covariant and generally covariant in the GR sense, both with respect to time and generalized space, generalized momentum. There's a lot of analogies between this approach and general relativity. And another maybe theme of this conference, I guess, is that if you're thinking about GR, you may, instead of thinking about manifolds with metrics, you might think about manifolds with their causal structures or a manifold with a conformal class of metrics. And well, I'm going to talk about Reb dynamics, and then I'm going to talk about contact structures and some kind of analog of a conformal class of dynamics, if you like. So, and that's what the second half is to do with. It's quantizing a contact structure, which is, yeah, maybe you can think of it that way. You want to think of quantizing all possible geodesics, but the metric modular conformal rescalings try and do all of those. And there's a lot to be won from that. Okay, the second half of the talk will be kind of more technical than the first. So let's see what happens. So here's a fun picture. This is quantum mechanics. Hey, look, I've got my first Schrödinger reference. There's the cat. I removed, I don't know, it's a generalized cat, so it's only got one ear. Here's what quantum mechanics is. You've got some laboratory. Here's your one-eyed observer here. And the observer lives in a classical lab. That's this big box. And the quantum system, some idealized quantum system. And we're imagining this to be independent of the lab. And the experimenter can do various things. The experimenter can look at the system. That's why the experimenter has an eye. The experimenter can, or maybe just has to wait so the system can time evolve. And the experimenter could do other things. The experimenter could turn on an electric field or instantaneously apply a rotation operator or something like that. And that's what these various dials and knobs in the laboratory are going to do. And then the experimenter will prepare a state and wait, and then observe the state again and compare it with some prediction for the state and calculate probability. So that's quantum mechanics. Okay. Those words with a few more equations. So the mathematically, we like to describe the quantum system in terms of a Hilbert space. And here are some of the experimenters, the experiments that our idealized one-eyed experimenter could do. So they could prepare an initial state and they could wait, and you'd get some unitary evolution here. Maybe they'd do something a little different. Maybe they'd apply some kind of rotation operator M. And then having done that, they'll have some final state and they'll take some inner product, because the Hilbert space after all has an inner product. They'll square it up and normalize it, and they'll calculate probabilities. Now, if we stare into the eye of this formula or that one, better this one a little bit, you might say to yourself, oh, this evolution operator, what is it? Well, if this Hamiltonian here was time dependent, which it well could be, then you're going to have to do some kind of path ordered integral here, not just the exponential for time times the Hamiltonian. And well, then you, having seen that, you ask yourself, what does this formula look like? And you might come up with the answer that it's a some kind of line operator. I'm just wondering, is there a chat to this? Because when I teach calculus, the best part of doing it online, the best part of it is reading the chat afterwards. Because if you want to ask questions, you could put it in the chat or screen. Okay, so let's suppose we do believe that this operator here is a line operator. Well, then what does a line operator typically look like? It ought to be a path ordered exponential of some object A hat. Well, that's a connection or a connection form. It's what we do holonomies or parallel transport with in Yang-Mills, if you like. And in particular, so you would have to have a connection, and this integral would be an integral over some path. Now you might say, oh, well, the path here was just a line being time, and time just marches on. But not everybody's going to agree on what they think time is. We know that in GR. So we would like some kind of covariance, and we might want to be more open-minded about that path. Also, what is this operator going to act on? Well, it's going to act on sections of some kind of vector bundle, the space where matter fields live in Yang-Mills theory, I guess. So if we really believe that that's a line operator, there are various ingredients that we would need. So if we have a vector bundle, one ingredient would be the base space. And what ought that be? Well, I kind of want the base space to correspond to, it's the place where paths happen. And these paths are these experiments. Maybe this picture is, this picture could be quite good. They correspond to classical things in the lab. For example, if you did this rotation here, well, this operator here may well be quantized and have an interesting spectrum, but this angle here is a real number, and that ought to be some coordinate on some manifold. And again, this time coordinate ought to be some coordinate on some manifold, which will be the base of some vector bundle in this picture. So in fact, I want the generalized laboratory to be a manifold which labels all possible generalized positions, momenta, but also time. So I'm going to describe that by the portmanteau. I don't know what a portmanteau is, but I've been told it's a word that you use when you do the German thing of joining lots of words together. Funnily enough, portmanteau is a French word. It's all very confusing. Anyway, let's call this a phase space-time. So it's a phase space with time. It's going to be necessarily an odd dimensional manifold. And I've drawn a nice picture of it here. I'm going to call it Z throughout the talk. And I'm going to think of it as the lab, and experiments are going to be paths in this space. I've drawn it rather groovy, like with holes and three ends, etc. And you can have all sorts of interesting discussions, like if time was somehow, generalized time was going that way, would it be okay to put a cap on this space? Or would it be okay to sort of close that off? And is it okay to have loops like that, etc.? Well, cycles you probably do want, because we often have like periodic coordinates. I don't know whether you want time to end. That seems a bit depressing, but you can think about that. Okay. I just looked at the corner of my screen and I noticed it was 9:41 a.m. Tuesday, January 9th. I think that may be the time that I first gave a Zoom lecture. All right, let's talk about the vector bundle that we need. This generalized line, or this line operator here, is going to act on, well, up here it states in a Hilbert space. So this vector bundle, its fibers had better be some Hilbert space. So we want a vector bundle whose fibers are Hilbert spaces, aka Hilbert bundle. And so here's the picture. Let's call that thing HC. Here's your laboratory down here. Here's your Hilbert space up here. That line operator is going to do unitary transformations. So we'd like the structure group of this thing to be U of H, unitaries. See how I said the word unitaries and then I wrote it down. It's a great way to give a talk, I'm thinking. What else? Yeah. So the line operator is taking a state here in this Hilbert bundle. It's associated to some connection nabla, and it's going to parallel transform it, parallel transport it. So parallel transport from some initial lab point P to some final one Q to some other state. Let's call this I prime. And then the experimenter will do some overlap and calculate probabilities. So this picture is, it's not changing regular quantum mechanics. It's just describing it a little more geometrically. But in a way that's, well, everything's nice and clear now.
Can I ask something?
Yes, you can.
Or object, maybe. So usually these vectors in like some wave function representation would be functions of the base, the point in space. But now this point in space is part of your Z. So
yeah. Yep.
So how does this? If you say it doesn't change so much, I don't understand why it doesn't.
So let's. So the Schrödinger equation. I did it again, Schrödinger. I'm nailing this. I'm so happy. The Schrödinger equation here is a parallel transport equation for sections of this bundle. So you're right, nabla psi equals 0. Now, sections of this bundle are going to depend on two things. Well, if this is a Hilbert space, this might be L2 of R, for example, and the coordinate here might be S. So as a function of this coordinate S, these sections will be just regular wave functions or states in the Hilbert space. But they're also going to depend on points in the base space. And these points, if you do choose coordinates, you might call one of them T, you might call one of them X, you might call one of them P. So they'll depend on T, P, and X. And now, if you ignored the P and X, this would be the normal thing you do in quantum mechanics. Like this equation would look like d by dt acting here, plus some kind of Hamiltonian acting on those variables. But now we're being more open-minded because we're saying, well, what you think time is and what I think time is might be different. My time could be some combination of this position and that time variable. So I want to make some general coordinate transformation. And so I'm just writing wave functions that depend on all these possible coordinates. But the regular picture is embedded in this one.
So you say you take flat sections and then you recover it.
Yes, you can say flat. I think the right way is that to say this equation is it's the parallel sections. So if a connection kills a section, you call it parallel. I will require that this connection here is flat, so that parallel transport has a good solution. If I hit this equation with another nabla, I don't want to get some integrability condition. You do want that. So you'll have a flat connection, parallel sections.
Does it give some restriction on the Hamiltonians?
No, but it will give you more Hamiltonians. Because the experimenter back here could do a lot of things. They could have a Hamiltonian for weighting. They could have for Hamiltonian for turning on a magnetic field. They could have for Hamiltonian for translating the system. And it'll give all those Hamiltonians. So it's like it's the evolution for all the Hamiltonians packaged into one nice system where everything is covariant. That's the way to look at it.
Interesting.
Okay. Hey, look at that one. I scribbled all over that, which means I probably talked about it. Graffiti is a thing of the past. I think that's the message. Okay. I'm going to make a kind of definition here. I'm going to make quite a few definitions. This is a definition that just captures that picture. I have a thought at the back of my mind a little bit, which says, like here, we might talk a lot about quantization, but quantization, a lot of the time, is just our attempt to grapple with quantum mechanics. The quantum mechanics is just there. We like to get it from some quantization because then it gives us a nice understanding of the quantum mechanical system. But you could have a quantum mechanical system just sitting there and nobody quantized anything per se. So such an object I'm going to call a quantum dynamical system. So what would that be? I want the data of a Hilbert bundle. I want a flat connection on this Hilbert bundle. I want the structure group to be U of H, as I mentioned. I want the Schrödinger equation to be parallel transport. Generalized wave functions are sections of that Hilbert bundle. And there's a little thing that I put here. I divide by holonomies because I said that I wanted parallel transport to give these solutions to the Schrödinger equation. And back here in my picture, I said, well, it could be that they're loops. And so it could be that even though you have a flat connection, the holonomy of line operators is non-trivial because this manifold has a pi1. So pi1 fundamental group of Z.
Andrew, sorry, just one moment before you went to this. Would it be correct? Okay, the picture you're drawing reminds me very much Fedosov quantization. So if I choose polarization, I can also take a bundle of Hilbert spaces over each point. Of course, you have time in your phase space, but this is not
let me write some words, because this stuff here is very motivated by Fedosov, and it's very close to Fedosov. So if you were to just run the Fedosov picture, not for Poisson, but a contact manifold, you would land on this. That's one comment. Second, it's also very motivated by stuff that Maxime and Xavier were doing for higher spin and Fedosov BRST type pictures. And basically, a lot of what we did was mimicking that in this contact setting. So it's just absolutely right what you say. This is very Fedosov. Also, Fedosov has this Weil bundle. So here we're talking about the Schrödinger picture of quantum mechanics. If instead you did Heisenberg picture, that's akin to working in the adjoint bundle. And that adjoint bundle would essentially be, if you worked formally, like formal power series in H bar, that would be the Fedosov Weil bundle. So all those things are here. That's right. Okay. What's happening now? We're here. Oh, yeah, I was mumbling about this holonomy. Like I was saying, well, it could be that this manifold has a pi1. And that's actually a good thing in a way, because even if you go ways back here, it can well be that you have operators that get quantized. And the reason that they get quantized is, well, there's some boundary conditions. Like if you do translations on a circle, you expect the spectrum of that operator to get quantized. And that quantization is this holonomy coming from the pi1 here. And in principle, I need to divide out by it to make sure I get a nice unique solution to this parallel transport Schrödinger equation. So this picture picks up global aspects. Okay. Next is an example. This is to touch base and check that I'm not just rambling about crazy nonsense. Formulas. Later on, there'll be too many formulas. So far, there haven't been enough. So here's an example. It's the enharmonic oscillator. Let's put an enharmonic oscillator. So quantum mechanics on a line, but let's make the line a circle. This is my generalized phase space. So I'm going to have my position coordinates called theta here. It's on a circle. I'm going to have some momentum P. That's on a line. So that's the first R of its R2 here. And then the next R is time. I've written this here. And in this picture, you have to pick a Hilbert space. And the Hilbert space, the natural one to pick here is L2 of S1. If you don't make this S1, if you were to put R there, this holonomy stuff that I was talking about would force you to put an S1. It will do the quantization for you. And wave functions or elements of this Hilbert space are just functions of theta with some square integrability. All right. Then this operator here, this connection on the Hilbert bundle is going to start off with exterior derivative, D plus some A, and here's A written here. It's a one form, taking values in operators on the Hilbert space, and you can see them multiplying by theta. So here's the potential. So multiplying by functions of theta is the acts on this Hilbert space, and taking derivatives acts on that Hilbert space. And then all this stuff has been kind of designed, and again, in some kind of Fedosov way. If you're right, it's Fedosov BRST for higher spins. Formulas with these kind of shifts also appear. Anyway, it's all designed such that this thing squares to 0. So you're taking another nabla, and this gives just an integrability condition. This is my generalized Schrödinger equation. And you might have anger because it's 3 Schrödinger equations. It's a one form's worth of equations, an equation in the d theta, dp, and dt direction. But the fact that this nabla squares to 0 implies that these are all consistent with one another. So you can integrate out 2 of these equations and just return. If you really like evolution in the time direction, you can just return to the time component of this one form, integrate out the other 2 equations, meaning solve them, and you will get the harmonic oscillator Schrödinger equation. There's another feature of the way this thing is designed. I should have perhaps put a little label H bar in it because it depends on, it's a one parameter family of connections. And in the limit H bar goes to 0, you can kind of see there's a P d theta here, looking at the leading H bar dependence. There's a 1/2 P squared, and there's a V of theta here. And that is the classical Hamiltonian. So the classical mechanics, or maybe that's the classical action for the system, P d theta minus 1/2 P squared plus V dt. So the classical stuff is inside this connection, and it's given by its leading H bar dependence in a Laurent series in H bar. Strictly speaking, it's a Laurent series in root H bar, but that's a small detail. Okay. That's probably enough to say about that. I'm going backwards. So I've told you what a quantum dynamical system is. I do want to talk a lot about quantization. So I do want to talk about what we're quantizing. So we're quantizing dynamical systems. Generally, what's a dynamical system? Well, it's some evolution. So basically, it's a manifold with a vector field telling you where, if you start at some point, where will you go? Not quite the way we want to say it in physics. So I want it a little different. I want to say that a dynamical system is some odd dimensional manifold. That's my lab stuff. And some rule for determining paths in this odd dimensional manifold. And I actually really do want unparameterized paths, just like you do for maybe, think geodesics. Geodesics are unparameterized paths in general. And so the structure you need is just an odd generalization of a symplectic manifold. This definition here, it's not the one you will always see for odd symplectic. Sometimes people add one extra condition that I don't happen to like. If you look at this condition, no, it is exactly the symplectic definition. So a symplectic manifold is a manifold with a closed two form, and that two form is invertible, i.e. it has maximal rank. And so it's exactly the same condition, just with the thought that maximal rank for an odd dimensional antisymmetric matrix allows you to have one zero mode, one eigenvector. So there's a non-trivial kernel for this two form. And then you just ask that paths solving the dynamics are paths whose tangent vector gamma dot lies in the kernel of this two form. The other thing that's nice about this definition is that for physics, we love to have an action. If this is closed locally, I can always write it as the d of an alpha. And so if I've got some path and I'm making small variations, then I can write in that little patch, I can write an action, which is just the integral of this one form alpha over path. And that's the thing you want to quantize. And if you think about it, what action could be simpler than that? Integrate a one form over path. And this is as covariant as you could hope for. There's a kind of optimal version of this setup, and that's a so-called contact geometry. It asks that you're odd symplectic, but this phi, which I'll tend to call the levy, is everywhere exact. It's the d of an alpha. And moreover, the alpha is special. If you take alpha and you wedge it n times, so remember I'm doing z2n plus 1, if you wedge it n times with this levy, you get a volume form, and you ask that that never vanishes. Volume form is good because you can write various Liouville theorems. When that stuff happens, alpha is called a contact form. A phase space-time equipped with a contact form, that data is basically good enough to describe nearly any classical mechanical system you could dream of. Okay, and a little bit of data about this stuff. There's a nice dynamics that you get. So you ask that the tangent vector gamma dot to your path is in the kernel of this two form phi of the levy. Since you've got a distinguished alpha, you can, if you wish, normalize this vector and ask that alpha of rho is 1. Now, sometimes a odd dimensional manifold equipped with this contact form alpha, that's called a strict contact geometry. If you only have the information of the kernel of this alpha, in other words, you have a hyperplane in each tangent space or a hyperplane distribution, which happens to be maximally non-integral because of this formula, that's called a contact distribution. And that is a contact geometry. So let's distinguish here. Reb dynamics, you have a given contact form. If you only care about the kernel of alpha, then you only care about the contact form modulo rescaling. So alpha will tilde alpha with an omega squared alpha. And that will determine this contact distribution. And that's a contact geometry. That's the thing that knot theorists like quite a lot for three manifolds. And your GR conformal geometry detector should be going off, because metrics modulo conformal rescalings, the analog here is contact forms modulo conformal rescalings. How do you quantize such a thing? This is a kind of summary. So you got the data of a strict contact geometry. You put in the information of some Hilbert space. That's part of your data. There's some string of bundles you can make. So this distribution of the contact geometry, that comes equipped thanks to this Levy form phi. It comes with an anti-symmetric metric, if you like, or an anti-symmetric bilinear form. So you can look at frames. You can look at symplectic frames. Well, once you have frames, then you have, so the group of frames will be SP2N, then you have a principal bundle. It's just there. Then what you can do is actually where I wrote projective metaplectic, that ought to have been over there. This is terrible. It's not readable anymore. Anyway, now you've got an SP2N bundle. Now, if you are so lucky as to have a representation of a structure group, and here I will use the projective metaplectic representation. What is that? That is just this thing. If you have a harmonic oscillator, the metaplectic of SP2 is the thing generated by A squared, A dagger, anti-commutator, and A dagger squared. That's an SP2. Projective means I'm acting only on rays, and quantum mechanics, we care about rays. Okay, so you have that way you get a new bundle. That's our Hilbert bundle. It's the associated vector. Then you look at the frames on that bundle. If you have a Hilbert space, it's got an inner product, and now it has frames. Now the frames are quite big. It's the space of all orthonormal bases for the Hilbert space. So that could be quite big. And that will give you a U of H bundle. And then you can again associate, and then you'll get this Hilbert bundle HC. So this Hilbert bundle is just there once you have a contact geometry, and that's a reason to like it. So the Hilbert bundle you just have, then your job is to quantize this system with its Hilbert bundle. It's to find this flat connection, nabla H bar. Actually, you want to find a one parameter family of connections with a nice regularity property. With the regularity property, actually, you want it to have a Laurent series in root H bar. The square root of H bar is just there for silly convention reasons. I can explain more later if you need, but you want that the leading part of the leading term in a Laurent series for this connection is the contact form alpha. And then that's a quantization. Note, a connection always starts with the exterior derivative, but this is producing a one form because the exterior derivative has no H bars, so it's not the leading term. Okay. How do you get such a thing? Well, that can be done using BRST and Fedosov methods. How am I doing for time? Probably not too bad. Here's just an idea. There's an old idea of Witten, which says, suppose you had the integral of a one form along a path. How would you quantize that? And he asks it in the simplest setting. Suppose the one form is the d of a Morse function. Well, if you write df, that is really, it's dif z dot I. That's what you're integrating. And in this system, the momenta pi are constrained to be the derivatives of this function. So if we're on a manifold of dimension 2n plus 1, there are 2n plus 1 constraints. They're first class. And then what you do is you run BRST. And the answer is that the BRST operator quantized is this operator. It's just the ghosts become one forms. The BRST operator is a twisted. It's a kind of trivial twisting by the Morse function. It's a twisting of the exterior derivative. And then you're off to the races because you do de Rham cohomology. So we're in that Witten situation, except life is a little bit different. We don't have dif z dot I. We have the integral of alpha I of z dot I. And if you analyze carefully, you'll end up realizing that you don't have 2n plus 1 first class constraints. You have maximally the opposite situation. You have one first class constraint corresponding to reparameterizing the world line and 2n second class ones. Well, there's some BRST methods for handling that. At the end of the day, when everything settles, well, there's a trick where you try and turn the second, you work on a larger space, and that's where that Hilbert bundle is coming from. You work in a larger space where the second class constraints become first class. This is Fradkin et al. This is their idea. And on that space, you eventually end up with a BRST operator that squares to 0, and it just ends up being the nabla I was writing. There's some conditions on this operator. Its leading term, connection. Its leading term has the classical information of the contact form. The next term in a series in root h bar is related. Well, it's related to the Heisenberg algebra. And there's a bit of Stone von Neumann going on. There's also a little bit of so-called symplectic spinners a la Constant going on here. I should probably explain a little bit. Everything here looks a little bit like GR. So think about, if you were to think that these kappas were Dirac matrices, and you were to write that the anti-commutator of Dirac matrices, gamma mu, gamma nu, was equal to the metric. That's a nice move that you can do on a manifold that's spin. We're not dealing with metrics here. We're dealing with symplectic geometry or contact geometry. So instead of a metric on the right-hand side, put the levy. And then ask that instead of an anti-commutator, you get a commutator of some kind of symplectic Dirac operators. This is this map here. Another way of saying what's going on is a Hilbert space always has up to unitary equivalence by Stone von Neumann. There's a representation of the Heisenberg algebra. And I'm asking that that appears as the next term in this Lorentz series. If you run Fedosov games, then you work formally in H bar and try and find all these terms such that Nabla is flat. I would advocate, although that's very hard, that you should always, if you can, try and not solve formally. If you can really solve for a bona fide connection, not just a formal expansion, then you have a quantum dynamical system in the sense that I wrote down. Okay, now what I want to do is soup this business all up to the case of not strict contact or quantization of Reb dynamics, but I want to quantize the whole conformal class of alphas. I want to quantize a contact geometry. Motivation for this is, well, one is just a gut feeling. It just says we know this is good in GR. So it's got to be good here because there's a lot of symmetries of the system that we're just going to uncover. Second is more math, is that people really like contact manifolds, and there are big open questions like, are there periodic Reb orbits, the Weinstein connection, et cetera, et cetera. So can we put some extra data coming from quantum mechanics on contact manifolds to better understand them? I guess you've had the tractor stuff. I'm about to do tractors for contact. If you're doing conformal geometry tractors, it's all for orthogonal groups. You can almost take every formula there and replace the orthogonal group by a symplectic group. Most of them carry over. I'm doing something that will make the tractor people angry, but we couldn't resist it. Tractors for contact geometry, you should call them contractors. It fits with the whole tractor machinery sort of analogy. Quick reminder of tractors and how you could get them. So in GR, you have a manifold with a metric that's Riemannian, manifold with a conformal class of metrics. Then the first thing you should do is think of this data as a manifold of one dimension higher. So each metric has associated with it a whole R plus worth of metrics, meaning that at every point in this manifold, you get a ray. So you should think of this, well, you might call it a ray sub-bundle of the cotangent bundle or something like that. But what you want to do is think of the data of a manifold with its conformal class of metrics as some kind of cone like this. And the actual Riemannian geometry comes from taking a section of that cone. So I'm going to start thinking that immediately. And when I write this, I'm thinking of a cone. And this cone is really it's the total space of an R plus principal bundle because you can slide things up and down this cone. This is the conformal rescalings. And then the good game here, according to Fefferman and Graham, and really Dirac, I guess, if you go back far enough. Other people have milked this. Maybe Itzhak Baz does this a lot. This gets used a lot, this picture, but you want to embed this cone in an ambient space of one dimension higher. Okay. And then all sorts of nice things happen. If you want to understand what the tractor bundle is, you look at the tangent space to a point on this cone. This tangent space, modulo rescaling it or sliding it up and down the cone using the natural R plus action given by these rescalings, that is precisely the tractor bundle. And I want to run the same game for contact. Oh, incidentally, you must add some data to this space. You add a suitable so-called ambient metric. You can try and make this ambient metric unique by solving a Ricci flat condition here, but you don't necessarily have to. You might work with a class of ambient metrics. The key thing is that you want these to have some kind of exactness condition. This X is precisely the vector field, generating this R plus symmetry that slides things up and down and gives this symmetry. So let's run that ambient space game for contact. So if you take strict contact, Z with an alpha, you go to a contact geometry, Z with a conformal class of alphas, just like I did for the metric. Then again, you can think of this as a manifold of one dimension higher, and that often goes under the name of a symplectization. But I'm just going to denote it by Z comma alpha. And again, it's an R plus principal bundle. Now, the symplectization is nice, and if you're playing ambient space games, you can just use the symplectization as the ambient space for a contact geometry. Fox has a nice paper on projective contact structures, which does this. Gover, Nurser, and Wilsey do it as well and describe this in quite some detail. Also, I should say, if you're into this stuff, volume 1 of Cup Slovak, I'm not sure there's a volume 2, but that has some information on, well, on more general parabolic geometries, because after all, that's what we're studying here, than just the conformal one. Okay, so you should again embed this in an ambient space. So if Z was dimension 2n plus 1, I'm up to dimension 2n plus 3 here. And then you need some appropriate analogs of this structure here, the ambient metric. So you need an ambient contact form that somehow knows about the R plus action. You could try and rewrite this condition in terms of Lie derivatives. Having done that, you'll be motivated to write the following thing. Oh, I should say, by the way, that this cone here, once you have the ambient metric, is given by the space x squared equals 0, and you want an analog of that as well. So you want a 1 form such that an ambient 1 form, A of x, you want this thing to be contact, of course. You want A of x to give this cone. You want the restriction of A of x to any section of that cone to give an alpha in the conformal class of contact forms. And the analog of the ambient metric condition is this one. You want L sub x. You want a homogeneity property of this.
I'm a bit lost. Can you explain again what is capital A and capital X?
Right. So let's go back. In conformal geometry, what you do is you start with a metric, you go to a space of 2 dimensions higher, and you work with a cone given by g of x comma x, i.e. x squared equals 0. This cone is this space, okay? And the ambient data you need is this ambient metric. Now I'm going to do the same thing for contact. The downstairs data is a conformal class of contact forms. This is this bold alpha. The upstairs ambient data will be an ambient contact form A. This space here needs to have an R plus action generated by X. If I feed this vector field X into A, I get a scalar. I ask that scalar to vanish. A of X equals 0 is this cone here. A of X equals 0 is the symplectization. And then there's an equivariance property that this ambient contact form needs to obey. Did that help?
So this kernel means just where the function vanishes.
Yep.
0z of the function A of x.
Maybe Kerr is terrible. Maybe I should write 0. I agree. That's confusing. Okay. And again, the the picture is this before. You look at the tangent space in the ambient space and you slide it up and down the cone. That will give you the standard contractor bundle. I don't know how much you've seen, but you may have seen it already. I think Andy calls them these damn triples that they write. In conformal geometry, the tractor bundle is sort of the regular tangent bundle, and you add a pair of scalars. Strictly, they're not scalars, they're densities. Densities are, well, they are functions of the symplectization with an equivariance, with definite equivariance, with good rescaling properties.
Do you have a connection downstairs, or only?
Not yet. I will talk about connections. Connections is important, and often a way that people do this game is all through connections. I want to do the connections later, but I will get to connections. Okay. If you do know some tractor stuff, you will know that sections of a standard tractor bundle is a triple of some vector and two densities with some transformation rule that has something to do with a parabolic subgroup of the orthogonal group. And in fact, that parabolic subgroup is exactly the one that you need to divide the orthogonal group by to get the flat model as a symmetric space of that whole cone structure. And all that story, all that representation theory has a direct analog here. The parabolic here will be the right one. Anyway, here's some formula for what sections of this contractor bundle looks like. But as I said, an easy way to think of it perhaps is this tangent space modulo sliding up and down using the R plus equivariance. And this is kind of a nothing theorem. I think if you take the old Gova-Chup paper on ambient spaces for conformal geometry and just copy things, you'll be able to come up with this theorem. Oh, see here, I've made a slight lie. It's not the tangent space here. A is contact. So I want a subspace of a tangent space. I want the ambient distribution, which I'm calling capital C. So the ambient distribution of this contact form A, that is the contractor bundle. Its rank is 2n plus 2. Not 2n plus 3, which the tangent space would have been. Now you guys started late, didn't you? So I can still motor. Is that correct?
Hey, you didn't.
Okay. If you say nothing, I could be here for another 5 hours. Yeah, and you'll just come into the room and just laugh at that guy periodically. You're just like, he's still talking. Okay, now let's talk about connections. Let's go back to the strict contact setting. Sorry, the strict quantization, the quantum dynamical system that I showed you. This flat connection, the piece at order 1 over root h bar, I was calling it this calibration map, but really it's just a representation of the Heisenberg algebra. The flatness condition says that if you take this connection and now look at the piece at order, not h bar, not 1 over root h bar, but the piece of order h bar to the 0, then what you will find is a connection on the distribution. So quantizing a contact geometry or a strict contact geometry, part of your job is to pick a connection on the distribution. The formula for how you get that connection is just given here. It's by passing this nabla through this calibration map. Okay, U here is a vector in the distribution. And this is how this connection on the distribution, which I called C, acts on the vector in the distribution. Okay. I think when you try and get the Lorentz connection on spinors, there's a formula very like this that you may have seen. Or if you work with Clifford geometries, they'd write something exactly like that. Two other little pieces of data that I need. Once you have a contractor bundle, there are two special contractors in town. One is the contractor corresponding to this vector x. It's called the canonical contractor. The second is, well, this A, you can take the D of A and make a phi. There's a levy. And this levy now acting on this tangent bundle here, or this on this ambient distribution here, that gives you an antisymmetric bilinear form, which we will call the contractor symplectic form. So you've got the canonical contractor, the contractor symplectic form. If you do conformal geometry tractors, this would be the tractometric. It's always good to pick a basis where this canonical contractor is one of the basis vectors so that it just reads 0, 0, 1, in which case your contractor symplectic form will look like that formula. And then what does it mean to be a connection on the contractor bundle in this language? So U is now some vector in the base space. The base space is Z, the underlying contact manifold. Well, you want some kind of Cartan condition. I think they call this a regularity condition, that if you act on X, that it returns the contact form alpha and the actual vector U. Back where we wrote that G tilde is equal to nabla X in the conformal picture, this equation's that equation, if you like. You also want that the contractor symplectic form is held parallel, and that's that condition. So this connection is a contractor connection. The contractor connection will be part of the connection that we build to the quantum, a quantum connection that we'll build to quantize the contact geometry. So let's try and do some of that. There's some Hilbert bundle picture. Let's go quickly. This a little quicker. The picture is very similar to before. You look at the symplectization. There's a nice sp2n plus 2 that acts on the tangent bundle. So you can look at symplectic frames again. Then you can do an associated vector for the metaplectic representation. Then associate again with respect to U of H. Then you'll get some kind of Hilbert bundle, but a Hilbert bundle for the symplectization. And this is kind of a halfway step. Like part of your answer might be to write some quantization over the symplectization. And that I've defined here. So let's call this a symplectization quantization. What a name. Anyway, that's the following data. You take this Hilbert bundle, you look for a connection on it that's flat and whose leading regularity structure, its leading term in a Laurent series gives, well, not, I could have written a bold alpha. It gives the Liouville. I need to explain a tiny bit here. If you have a symplectization, the symplectization is the manifold, points of which are contact forms, modular rescaling. So there is a tautological one form given by the contact form at that point. We ask that that appears on the right-hand side of this limit. So this is the classical limit, if you like. Now, the last move really is to impose some R plus equivariance on this connection and divide out by it. And that's what's written here. Looking into the future. Oh yeah, we're pretty close. Right, so R plus acts on the symplectization. That's how it was defined, really. There's a nice vector field that generates that. And the idea is that the contact quantization is the symplectic quantization that I wrote divided by that R plus action. In more detail, there's two things going on. You've got a one parameter family of these connections on the symplectic quantization. You want some kind of flow with respect to H bar, or maybe some grading if you like. Fedosov always uses a grading, and this is his grading. This flow kind of should make sense, I think, because what is what is quantization, or what does it mean to have an H bar in the system? It means that there's some parameter, which we always call H bar, and you can flow it to H bar equals 0 and get the classical mechanics out. But the actual quantum system, that exists for some non-zero value of H bar. And you can see that I don't really want H bar to be just formal here. I would love it to be a full solution, if you can. All right, also, I got some connection on the distribution by taking the order H bar to the 0 part of a connection. I do that again, and I feed to it this vector X. There's a little bit of explanation here. If I would like to divide out by a Lie derivative to get R plus equivariance, this Hilbert bundle, sections of it are so-called symplectic spinors. Think about how to do Lie derivatives on spinors, and you'll realize that you need a connection. The Lorentz connection will do it, then that's what we normally do to get an analog of Lie derivatives on spinors, i.e. I want to get an action of the R plus, I want an action of this R plus group on sections of this Hilbert bundle. So I take this connection, the Nabla-Nord piece, which is a good connection on the distribution, feed it to X, add this grading piece, and then ask that that commutes with this symplectic quantization connection. That's the correct notion of R plus equivariance, I claim. I take this Hilbert bundle over the, this is a Hilbert bundle whose base in the symplectic quantization, so the base here, is Z comma alpha. It's a manifold of dimension 2n plus 2. I need to get the base down to Z. So I divide out by the action of this connection here. That gives me a new Hilbert bundle. I'll call that the Hilbert contractor bundle. There's an associated vector bundle construction of it as well. And then this data here, so that connection modulo this and this bundle, that's the contact quantization. It's a definition, if you like. A nice thing, okay, is where do you get such things? Well, you can get it from that ambient quantization, and that's what this slide is trying to tell you. So you take an ambient space, so this is strict, you take the ambient space, which just has a given contact form. You do the strict quantization, or what I call the quantum dynamical system there. If you're so lucky to have such a thing, so this would be an ambient quantization. And you have this condition, that should be a tilde, that this connection obeys an equivariance, that one. This is designed to make this stuff here work, I guess. This data gives you a contact quantization. Going from GR to conformal, going from quantum mechanics of a classical system to quantum mechanics of a contact manifold. It's that analog here. Maybe getting close to a last thing to say. There's this beautiful theorem in conformal geometry. You've got a tractor connection. You should ask, what do parallel sections mean? Well, when you have a parallel section, you can form a density from it using the tractor metric and the generator of the R plus action. They always call this sigma somehow. Then you take the conformal metric, divide by that density squared, you get a bona fide metric, and that metric is Einstein. That's Bailey, Eastwood, Golver. So we would like a kind of analog of that. We would like to understand a little bit what it means to have a parallel section now. So a parallel section for the contractor connection, again, allows you to build a scale, but now through not the tractor metric, but the contractor symplectic form. If this density is everywhere positive, I can take the class of alphas and divide it by sigma squared to pick out a distinguished alpha. Then from the contact quantization, I pick out a special quantization, and that quantization will be the one I started with. This closes the circle. This will be the quantization of the Reb dynamics of that alpha. Roughly speaking, conformal plus parallel tractor gives Einstein. Contact quantization plus parallel tractor gives quantum mechanics. That's the message. I think I can finish. I could send people the slides if you want. The last thing I wrote down was just details of what things look like for the contact 3 sphere. And here I've solved the, this was with a lot of help from Xenia, actually. He'll recognize some of this stuff. But take the contact 3 sphere, solve for the connection, the quantum one, and then look at the contact version of that. This is a whole bunch of formulas, but you can just see all this stuff happening, and it's a bit more concrete, and it's kind of fun. But I think I'll just flash that past and stop here. So thank you.
Thank you, Andrew. Questions?
Sorry, this contractor bundles, this is basically the usual tractor bundle that
yes.
people associate to contact projective structure.
Yes, very close to that with one small bit of fine print. So when you do contact projective, there is this, that's a parabolic geometry, and there is a normal Cartan connection. And so there's an extra piece of data. I'm not using that normal condition. The reason is the normality condition gives you some connection on the contact distribution. When you do the quantization, you get a connection on the distribution. It may not be one coming from a contact projective structure, but modulo that small change, the answer is yes.
You have something like the contact geodesics, so you should also have something like that on your manifold.
That's what Fox does. No, that's what I'm not wanting to do. That would be the contact projective story. I like the subcontractor joke, by the way.
It may be related to like absence of torsion, actually. It's just modification.
Yeah, that is correct. There's some kind of torsion condition that you have to put, and you may not want to put that condition on the connection, depending on which quantum mechanics you're trying to get. So here you solve geodesics.
Other questions? Thomas?
What is the advantage of this ambient quantization over your contact quantization?
Oh, two ways to skin the same cat. Sorry, Schrödinger. It's probably the cleanest, in a way, it's the cleanest construction. It gives you a method to construct contact quantization. So imagine you have strict contact in dimension 2n plus 3, and that strict contact has a homothety. It has an R plus action. Then if you can quantize that structure, you immediately have quantized a contact structure in 2 dimensions or less. And that is nice. It's also at the back of my mind, I know the ambient space is fantastic for conformal. It's just been terrific. I think it should be the same here.
Okay. Actually, yeah, hi Andrew, I'm Boris Kruglikov. I have 2 comments and 2 small questions. So two comments is just like, first, you were talking about simplicizations. You made some references, but I think like actually this thing was invented by Arnold, and it is actually in his classical mechanics.
Oh, that's great. If you like, I think contact is fantastic and a great place to start. And this adding this extra direction, that is an.
I think he writes the formula. So
and if you like any of his stuff, there's an appendix in Arnold's book, which most people don't read, but it's really good. So that would be a great starting point. Yeah.
And second comment is that like you asked about parallel tractors, and that actually was asked by Boris Dubrov after the lecture of Jan Slovak yesterday, and we have some discussion also here in the coffee break.
Contact?
Yeah, well, it was symplectic, but yes, it's very related. So the question, can it be related kind of to give some kind of Einstein equation? But the thing is that this is going to be kind of underdetermined equation, underdetermined, right? So contrary to parallel tractor being overdetermined.
Yeah, so what happens, I could write some formulas, but if you know some things, if you look at the conformal tractor connection, that's essentially built from the metric, the Levi-Civita connection, and the Schouten tensor. And there's a contact analog of the Schouten tensor. In conformal, you end up asking the trace-free Schouten tensor to vanish, and that is the Einstein condition, you see. Here, there's a contact Schouten tensor, and it just is turned off. That's the equation you get from the parallel tractor condition. So it's contact Schouten flat is what the parallel condition gives. Oh, sun is killing me. 1 sec.
Now, small question. You said at certain point then to do Lie derivative of spinors, you need connection. I didn't understand this actually.
Yeah, how are you going to take a Lie derivative?
Natural.
How are you going to take a Lie derivative of a spinor?
Just covering, right? So it's local operation. So you can do it. It's not abstract vector bundle, right?
Yeah, maybe you're right. I have a second justification for this, though. Another way to say what a tractor is in the ambient picture is it's sections of the ambient bundle restricted to the cone and subject to the condition that nabla sub x, where nabla is the Levi-Civita connection, that nabla sub x on the tractor is equal to W times the tractor. That's the condition I'm doing. And I want to think of that as some kind of Lie derivative. If you just do vectors, you can convert that straight back to the Lie derivative. I don't know how to do that, but maybe you're right. Maybe I can do that for the symplectic spinners. I don't know a formula for that, though.
So last question from me. So that you made some computations for like standard sphere. Don't know. Do you use that it's kind of homogeneous, right? Did you try to do with some other contact thing like over twisted sphere?
Yeah, this is project list. I have a student thinking about all these things because on the S3, we were quite happy about this. We could solve beyond formality to all orders. And it would be great to have other models we can do that. Right now, we have 1 or 2 very simple models where we can. Not much more. But yeah, questions like that, we would love to do. I think it's harder. But it would be super interesting.
Other questions? Yeah, Maxim?
Maybe very general question. Just in symplectic settings, in this approach, do you see or can you reproduce results of geometric quantification in the model?
So this connection.
You try that?
There is a relation.
It was very old paper by Fratkin and Linetsky, I think, like 80s, who tried to do this sort of thing.
So the geometric. So I would view things this way. Fedosov in some ways is superior to geometric because it allows you in principle to quantize all operators. The problem is that it's got this formality stuff. Geometric, you quantize less things, but at least you don't have the formality business. Geometric kind of has 2 pieces. It has this choice of polarization, and it does have a connection. The leading part of this connection the leading classical piece is the connection they use. There's a paper by Fitzpatrick on contact geometric quantization, and you will see that happening. But the leading part of the connection used here is the one he's using. The bundle's different, of course. But so yeah, there is a relation. I mean, I haven't gone into that in great detail, but the sketch of a relation, I think, is what I just said.
Okay.
So you, oh, by the way, you say Vinetsky, and what was the other one? I like to look up papers.
Very old Fratkin-Vinetsky, it was called something like DFV approach to geometric quantization, but essentially they were doing more or less the same as Fedosov. But they really sort of physical level of rigor, but more
Oh, that could be nice.
Real,
That doesn't seem to be.
Andreas has a question.
Yeah, I think Andy has a question.
Yeah, I just wanted to ask about the contractors one more. So the claim is you have a canonical contractor bundle associated to your contact structure.
Yes.
Is a choice that you make on which you impose certain restrictions, which are these non-deterministic conditions.
That's right.
And
So I'm not getting a canonical connection, but I am getting the bundle.
but in a way, the non-degeneracy conditions should be enough to get an underlying contact projective structure.
So I think I could always pick the normal connection and then just get it, sure.
No,
And that would be doing
it's unrelated. It's just, it's like if you have a conformal Cartan bundle and you use a non-conformal connection, you still get a conformal structure.
Are you saying I should first look at projective and then?
No. The question is when you have your choice of connection.
Yep.
Yeah. Then you get something like a contact connection, I suppose.
Yes.
And this connection has geodesics.
Yes. Yeah, that
But
is
if
there.
you want the connection in its own right, it defines a contact projective structure.
Yes, that's correct. That's there.
Is related in some sense to what you're doing?
Oh, that is part of it. Yeah. So that connection. So in the quantum mechanics, yeah, for example, suppose you did the harmonic oscillator and you did Fedosov. Fedosov will stop at grade H bar to the 0. And the last part of this Fedosov connection will be that in the contact analog that I was describing, will be that connection on the distribution, in fact. And then you could look at its geodesics and all that for sure.
Okay, so in a way, you just have to modify the normal connection because of, yeah, what comes later.
So I just don't impose the normality condition because not all quantum mechanical systems will want it.
Yeah.
Some of them can. And they might be, that would be a good thing to look at. It's also project list.
And is
Quantum
this
mechanics from normal connections.
I mean, are you aware of the fact that Fox works in a more general setting than the parabolic geometry machinery?
Well, I spent time with Fox. So Fox.
Because he allows contact torsion.
Yep, that's right.
We don't.
Yeah.
So he has a more general normalization condition. So it may be possible that this can be used actually.
That's probably right. So you could take one of Fox's contact projective structures and then ask, could you quantize it?
Mm-hmm.
So take that connection and then see, could you get all the higher order Fedosov terms? And if you could find any model, no matter how simple, where you could find like all those terms, I think that'd be nice.
Thank you.